Mm-hmm.
So it's a pleasure to have Daniel here with us. Daniel studied at IMPA, and then he decided to continue his PhD abroad. He went to Lyon and then to ETH Zurich. Before we were talking a bit about Zurich, and he was making me miss the city again. So today he's going to be talking about a very nice development he recently had with Martin and Tassion about supercritical phase of percolation on more general graphs. So please.
Thank you, Augusto, and thanks the organizer for the invitation to speak here. It's a pleasure to be back, at least virtually, in Brazil and in IMPA. So yeah, this work is based on this paper with Sébastien Martin and Tassion. And so let's just proceed to it. So let's define the framework where we will work. So we'll consider G an infinite connected and locally finite graph as usual. And we will declare an edge on this graph to be open with probability P and closed with probability 1 minus P, independently of each other. We'll call this law P sub P. So this is called the Bernoulli bond percolation. And we define the critical probability of this graph, or critical parameter, PC of G, to be the infimum value of P, such that the probability that G contains an infinite cluster is positive. So recall that an infinite cluster is just the open component on this graph that we obtain on the process above. So we know that if G is transitive, then for P bigger than PC of G, G has almost surely at least one infinite cluster. So here, a transitive graph is a graph where its automorphism group is transitive on the vertices. So if you don't remember it, you can think about this graph as a graph that looks alike everywhere in each of these vertices. And we also know that G is amenable, then for P bigger than PC of G, then there exists a unique infinite cluster. So this is a result of Eisenman, Kessler, and Newman in 1987, and was pre-proven. And this is a proof more of as a no by Burton and King in 1989. So we will use strongly this uniqueness in what's followed. So in our case, we will work with graphs of polynomial growth, but this study of general graphs started with the work of Benjamini and Tassion in 1996, which is called Percolation Beyond ZD, many questions and a few answers. And our work is inspired on one of the questions on the paper, which is the locality question. So we won't talk about that question today, but maybe in a future talk, we'll give you more details about that. So what we want to do is to work on a special case of graphs of polynomial growth. So these graphs, so a transitive graph of polynomial growth is such that all its balls, so we denote it by Bn, as they have a polynomial, at most polynomial growth n to the power d. So we know that by some works of Gromov and Trofimov, that in fact this exponent d is a positive integer, and that in fact the size of the ball is asymptotically n to the power d. So it means that the volume of Bn divided by n to the power d is uniformly bounded away from 0 and infinity. So there exist two constants such that this is more or equal than n to the power d and bigger or equal than c to the n to the power d for n large enough. So we consider in this case d bigger or equal than 2, which is equivalent to say that there exists in fact a phase transition, so that PC of this graph is more than 1. And in this generality of graphs, we know this is true by Domenico Pangos, Guamigrofi, and Severo and Jadan. It's a work where they prove that the phase transition exists under some geometrical conditions on your graph. On ZD, we know that this is true. For example, we know that PC of G is more than 1 when PC of ZD is more than 1 when D is bigger or equal than 2. So the first graph of polynomial growth we all know is the hypercubic lattice, ZD. And on this graph, what to study supercritical percolation, the main theorem we know, I mean, all the theory is almost based on this theorem, is the Grimmett and Marstrand theorem. So let's recall it. We'll consider D bigger or equal than 3. And we consider also, say, a plane Z2. And over this plane, we will consider again a thickened version of it. So we'll thicken this Z2 in all the directions by K. And we'll call this new graph the slab of thickness K. We denote the SK. So this slab, what we know is that the critical parameter of this new graph SK, I mean this subgraph of the ZD, this slab, this PC of SK converges as K goes to infinity to the critical parameter of ZD. So why this result is important in the, also first, how can we prove this theorem? So the main ingredient, or one of the main ingredients to prove this theorem is the isotropy of ZD. So what does mean, what does implies is that, for example, if we know that the probability of crossing from having a crossing from this small box to this big box of open edges, so this red path, see, if this probability is bigger than 1 minus epsilon, what we can do is, since this box somehow is invariant by rotations, we can choose any of the faces of this box, and using the so-called square root trick, we know that the probability that this box is connected to one of the faces that we can choose is bigger or equal than 1 minus epsilon to the power 1 over 2d. So if this is close to 1, we know that this probability is also close to 1. So this is one of the main ingredients to somehow guide the exploration of the infinite cluster, because we can more or less choose some targets and try to guide this cluster along the way. So let's remember this property of isotropy. But how can we use this Grimmett and Marstrand theorem to show something in the supercritical regime? So this is a theorem of Chayes and Newman of 87. So that was dependent on this Grimmett and Marstrand theorem that was proven afterwards. And what it says that if we consider P bigger than PC of ZD, then the probability that 0, the origin, is connected to the border of the ball of radius n, but is not connected to infinity, decays exponentially fast. So this is called as the supercritical sharpness. So let's give a quick proof using the Grimmett and Marstrand theorem of this theorem. So we'll consider a P bigger than PC of ZD. So since we know that the critical parameter of this slab converges to PC of ZD, we can choose K large enough such that this P is actually bigger than PC of SK. So we percolate on the slab. So we consider Q to be the probability that 0 is connected to infinity on the slab. And since we percolate on the slab, this probability is positive. So let's consider again a box of radius n. And since we know that our graph is, we have invariance by rotations and everything, as we said before, we can actually say that, suppose without loss of generality, that 0 is connected to this face of the box. So what we can do now is to stack some of these slabs on the box. So we stack this somehow region, a portion of the slab on the box of size k, So these are just copies of this slab SK. And we can focus now on the exploration of this path, of this red path. So we can focus on these points here. So these points are, by definition, the last point where where this red path enters the slab. So this defines somehow a Markovian process, but it's not relevant at this moment. But what we can observe is that if 0 is connected to the box, but it's not connected to infinity, it means that each of these points is not connected to infinity. But by translation invariance, we know that the probability, for example, that this first point is not connected to infinity is just is more equal than 1 minus q, because with probability q, 0 is connected to infinity. So repeating this process for all these other points, we know that there is, in this case, m point, which is just n over k. So the probability of the event above is just more equal than 1 minus q to the power m, where this m is n over k. And this is just exponentially small in n. So this term here. So that's the proof of this supercritical sharpness using the Grimmett and Marstrand theorem. So, okay, we know that we can do a lot of interesting stuff on ZD, but what happens in more generality? So we know that in this hypercubic lattice, we have some isotropy and we have slabs. So you can use this Chayes and Newman theorem and conclude. But if we change a little bit the geometry, so suppose the easiest thing we can do is just to change the system of generators of ZD. So we consider a different Cayley graph of ZD with generators. So in this case, we consider these other generators, this smaller diagonal and this other big diagonal, which still generates ZD. And if we choose correctly these generators, we lose the isotropy, and we can still define some sort of slabs, but they are not useful to prove this Chayes and Newman theorem. And so this is another class of graphs which are still of polynomial growth, but we lose some properties that are important to us, and we can even go further in this generality. So one example of polynomial growth graph, which is, say, a simple example which is not abelian, is the Cayley graph of the Heisenberg group. So here is not important to understand what this Heisenberg group is, but I just recall that it's this group of 3 by 3 upper triangular matrices with 2 generators and as a specific commutator. But the important thing is that this graph has no any kind of isotropy, and if you try to define this slab on this graph, you just get the whole space. So there's no way to define slabs, and all the techniques we knew are not available anymore in this context. And just some curious facts about this graph. So you see it's like a twisted version of ZD, and in fact its polynomial growth dimension is 4 instead of 3 as in this other case. I mean, for this example I given you here. And in general, polynomial growth graph Cayley graphs are very exotic in the sense that, for example, spheres are not connected anymore. So if you want to study cut sets, it's not that easy to get to them. So many properties that you have on ZD are not available anymore in this context. So what we did in this work was to try to create techniques that are more general, so that don't depend on the symmetries that we see on ZD. And so in this case, we don't have isotropy, we don't have slabs. And what we proved is we extended this Chayes and Newman theorem to the case of polynomial growth graph case, where d is bigger or equal than 2. So we have the same supercritical sharpness. And as a consequence, we also have this an extension of this Kesten-Jean theorem estimates the cluster size distribution of the origin. So we see that the probability that the cluster of the origin has size bigger than n but is finite is asymptotically e to the power minus c n to the minus 1 over. So we will focus on I mean, since we are not specialists in geometric group theory, we will try to focus on the case ZD, but trying to forget that we have symmetries. So all the figures I will present will be on ZD, but we will try most of the time to forget that we have this kind of rotation invariance and everything. So yeah, all the results that I will tell you are also valid more or less. I mean, it's not exactly the same result, but it has their equivalent in the polynomial growth case. But for just to keep this thing light, I will just focus on Z. And we will focus on this first theorem. So what we can do is, I mean, one of the most important tools to study this uniqueness to this supercritical phase is what is called this uniqueness zone. So let's recall some simple facts. So suppose we are in this we are in ZD or any polynomial growth graph case, and we have this infinite component, this infinite cluster C infinity. So suppose we choose like a box on ZD of radius m around the origin. So we know that if we let m grow to infinity, at some moment this m will touch the infinite cluster. So we know that the probability at m, this box of radius m is connected to infinity goes to 1. But let's consider now a second box bigger radius n. So what we can observe is that in this case, we see that between this box of radius m and this box of radius n, there is two clusters crossing these annulus. So this first cluster on the right and this other cluster on the left. But since the infinite cluster is unique, we can let this n goes to infinity again, and we know that at some point these two clusters will merge, because if not, we would have two disjoint infinite clusters, and that's not possible. So this leads to this simple fact leads to the definition of this event that we call uniqueness event or UMN. So the event where there exists at most one cluster in Bn that touches the small box Bm and the border of the big box Bm. So let's, what we have said is that the probability of this event UMN as n goes to infinity goes to 1. So this is just a simple observation. And what we actually need in this case is something that is more, so we need a quantitative version of this fact that we need a control on this probability. And this was proven by Cerf in 2015. So it's a similar statement. So that it says that if I consider P bigger than PC, then there exists an epsilon such that for all n big enough, it happens the following. So we'll consider these two boxes, one of size of radius n to the power epsilon and one of size 1 to the power 1 minus epsilon. So the probability that we have two disjoint crossings from this box to this other box is sooner or equal than 1 over square root of n. So you can see that in fact this event that is called this two-arm event is exactly the complementary of this other event, this uniqueness event. So in fact, you can say that the probability of this uniqueness event above is in fact 1 bigger or equal than 1 minus 1 over square root of n. And let's keep in mind this figure. So each time somehow you condition that you have two disjoint paths and you ask to have this uniqueness event, since there exists as at most one cluster that crosses these annulus, these two clusters will need to merge together. So yeah, let's keep this image in mind because we will use it a lot. So in order to prove our theorem in ZD, what we will do, in fact, is to reprove the Grimmett and Marstrand theorem, but in a different way. So we will divide so we will have established two cases. So one case is that, two complementary cases. This first case is saying that there exist 2 points in this small ball, which are this distance n to the power 1 minus epsilon, such that the probability that they are connected inside this ball is bigger than 1 over n to the power epsilon. So this says that the probability of this happening is not that bad. And the complementary case will tell us that the contrary, so that for every pair of points in this ball, the probability that they are connected together is smaller than 1 over n to the power epsilon. So we will realize that this second case is in fact it's not a possible case. I mean, it's just a case that appears in this case just to show what we want, but a posteriori, this second case does not exist. It's a fictitious regime. So what we want to prove is that for starting from any of these cases, we can conclude that the probability that we connect two boxes of size n to the power epsilon together on this domino, which are distance n, is bigger or equal than 1 minus epsilon. So we go from something that is, this completely small to something that is really, really close to 1. So the trick is that here we are changing the parameter where we perform percolation. So we're using parameter p plus 2 delta. And this is somehow what we call sprinkling in general. So we change our parameter, but since delta is, since we're working in this supercritical phase, we are allowed to do that when delta is small. So we will focus on the next, on this talk in proving these two implications and showing how to use this domino construction to actually normalize and conclude this Grimmett and Marstrand theorem. And yes, I forgot this. So yeah, using this, we will prove this slab result. So let's focus on the first case. So this tells us that this probability is not that bad. It's bounded below by this 1 over n to the epsilon. And what, it's a quite common technique to use is what is called the sharp threshold techniques that involve this KKL and Lagrange inequalities. Tell us that in fact, if we integrate this inequality from somehow p to p plus delta, we can obtain that the probability at p plus delta of connecting not now the points, but some boxes of radius n to the epsilon together, and that are these boxes are the boxes around these points. So the probability of connecting these two boxes together is now bigger or equal than something that is super close to 1. So you go from something that is not that small to something that is very close to 1. And this is this comes from the general theory of sharp threshold. So from that, how can we go to the domino result? So let's consider our domino. And so we have two boxes of size n to the power epsilon, which are at distance n. And what we can do is to consider now some other boxes in between them, which are of distance n to the power 1 minus epsilon and of the same size as the other ones. So what we have learned is, so we want to use this result above, and we know that we can connect two neighboring boxes in this figure with high probability. So you can use, in this case, you can use FKG, but we don't need to, because since this is very close to 1, you can just use high union bound and it works totally okay. So we know that we can connect these two boxes together with high probability, and these two boxes together, and these two other boxes, and these two other boxes together. So in order, I don't know if now you remember the figure that comes from this Serf's theorem. We know that around this box here, we have these somehow two disjoint arms. And we know that the probability that of having these two disjoint arms is really, really small. So, or you can say that the probability of having a uniqueness event around this box has probability close to 1. So what we can say is that we can actually pay a little price just to connect these boxes. So you can use a union bound to say that these two components are connected with some probability, and you can repeat on the other two neighboring boxes. So using that, you show that the probability of connecting this box to this other box is bigger than, so it's very close to 1, bigger than 1 minus epsilon, if you want to say. So here we just put p plus 2 delta, but this second sprinkling is not necessary. So we just use one sprinkling, and we obtain that probably this domino result we want. So the first case is not that complicated, and so we have seen how to do it already. And for the second case, what we want to do is to use a new argument that is based on this Hamming distance. I will explain in 1 second what it is. And from this result, we can obtain that the probability of crossing from this other big box of size n to the power 1 minus epsilon over 2 to n is again really, really close to 1. So how can we conclude? How can we use this to obtain the domino result? Is a consequence of uniqueness via sprinkling. So this is comes from a paper of Benjamini and Tassion and has been used in other contexts. So we won't speak about this in this talk. We will focus on this new argument. I mean, it's not very new, but it's new in this context. And okay, so we know that from that we can obtain the slab result we wanted. So we will focus on the last part of this talk on this Hamming distance argument. So let's go to it. So this Hamming distance is called some other parts exponential stiffness, and it comes from a known inequality involving the Hamming distance of an increasing event. So this was proven. I mean, it was established first in this paper of Grimmett and Pisa in the context of on random cluster measures. And this inequality tells the following. So it tells that the probability, so this is just the last step of the inequality, but the probability at p plus delta of this event A, which is increasing, is bounded below by 1 minus exponential of minus 4 delta, this expected value of the Hamming distance of the complementary event. So let's recall the Hamming distance of an event, of an increasing event in this case, is the minimum amounts of edges we need to switch its value in order to the event not happening anymore. So we will see an example in 1 second, but it's somehow a generalization of this pivotal edges definition. Here we need to change a certain amount of edges to actually switch from one state or to the other. So this technique has been used in the random cluster model in several papers. So in this paper by Dominique Manurescu, where they prove the sharpness of this model for Q bigger equal than 1. Again by Manurescu and Raufi, where they prove the sharpness now in the case of slabs for Q bigger equal than 1. And by Dominique Copin, Raufi, Tassion, and Tassion, where they actually give a new proof of, or a new way of calculating the critical parameter in the random cluster model PC of Q. So let's define the event we will work with. So we define A to be the event where the ball of radius n to the power 1 minus epsilon over 2 is connected to the border of the ball of radius n. So the event we wanted before. So I will make a figure. But what we know is that the Hamming distance of the complementary of this event is exactly the number of disjoint open paths touching this smaller ball and the boundary of the bigger ball. So if you recall, is the minimal amount of edges you need to close in order to switch from one event to the complementary. So yeah, if you think about it, it's exactly, I mean, by a mean cut max flow, if you want, this is exactly the number of disjoint paths, or by this Menger theorem, it makes more sense. Is exactly the number of disjoint paths touching these two boxes. And we will call this H of a complement just H. So, because just to simplify the notation. So we want, I mean, from this inequality above, what we have is that the probability of having this crossing, so probability of this event, is bigger or equal now that 1 minus exponential of minus 4 delta expected value of H. So H, again, is the number of disjoint paths that goes from this box to the other box. So in order to lower bound this thing, we need to lower bound the expected value of H. And in order to do that, what we want is the following. So this is just a remark. So we'll consider our box. And so in the box we had before. So we just do another drawing. And we know that there exists a deterministic set A. So this set A, if is the set of points we have here, such that with size bigger than n to the power epsilon over 3. So this is just a number we will need, such that they are at distance bigger than n to the power 1 minus epsilon. So you take somehow a net on this small, so n to the power 1 minus epsilon separated net on this smaller box, and you know that this has at least this size n to the power L epsilon over 3. So what we know is that on this deterministic set, by hypothesis, we know that the probability that these points are connected together within the ball is smaller than n to the power minus epsilon. So this is, we know that the points are not connected among them in the expectation, say. And, but since we are in a supercritical regime, we can use that information. So in particular, we know that there is a density of points of this set that we call, so this density will be exactly theta p of A, which are connected to infinity. So if these points are connected to infinity, but they are not connected together, so because this probability is really, really small, it means that these points are connected by disjoint paths to the border of the ball. So remember, we wanted to lower bound the amount of disjoint paths that crosses this ball. So this tells us that there is a big quantity of paths that crosses from this small ball to the big ball. So let's do the actual calculation just to see where this magic appears in some sense. So we know that H is bigger or equal than the number of disjoint clusters between this set A of points and the border of the ball, by definition. And we now would like to count the number of disjoint clusters. So this will be very equal than the number of points in A which are connected to the ball minus the points which are connected together. So the number of this, I mean, this is just a simple, this is just inclusion exclusion. And we can take expectation of that And we see that, so we take expectation and we see that this probability on the left is exactly this theta p. This means bigger or equal than theta p. So recall, if you don't recall what this theta p is, just a probability that a given point in a transitive graph, when you choose any point, is connected to infinity. So this is bigger or equal than the probability that x is connected to infinity, which is this quantity. And this is somehow where this negative information becomes positive, because we know that this the probability that these 2 points are connected together is small. But since you have a minus sign, this is good for us because we want to lower bound these things, so it's ideal. And we see that this whole expectation is bigger or equal than a theta p, so this density we defined before, times, and I mean, this is just lower bounded by a squared n to the power minus epsilon. So since this is small, this does not really affect this quantity on the left. So the expected value of disjoint paths going from the small ball to the big ball is at least n to the power epsilon over 4, which is big enough for our purpose. So this shows our theorem, and I think, I don't know, I think this is the last slide, but we just need to do, once we have this domino result, now, I mean, you can wake up, and because this is like the part everyone likes. So we will see how to actually now prove that we percolate on ZD using this domino result. So this is somehow called some context static renormalization, because the Grimmett and Marstrand proof use somehow a so-called dynamical renormalization, where your process depends on the path, so you do an exploration and so on. And here we can just use our domino result in a fashion that most of you already know. So we consider this small, I mean, this lattice of boxes of say the diameter n, and so here we are just studying the slab of size n, but seen from, I mean, just a projection on the plane. We consider these boxes, and we consider these model boxes on the centers of these balls of radius n to the power epsilon. So what you see here is exactly the domino we studied before. So we declare an edge xy equifigure to be open if the box of around x is connected to the box around y within this domino. And so this is not enough. We will ask that there exists uniqueness on this annulus around x and on the annulus around y. So let's see that this, in fact, so let's consider, for example, this open edge xy, and let's consider some other open edges around the way. So let's consider that we have somehow an infinite sequence of an infinite path of open edges on this new process. So what we have now is that, oh, it was too fast. So what we have now is that since we're asking that there exists uniqueness around, say, y in this case, having an open edge, this open edge and this other open edge implies that you have somehow two disjoint paths, if you have them. And in that case, if you have them, since you are asking to have uniqueness, they are actually one unique cluster. So it means that these two paths around y are connected together. And we have this uniqueness for every edge, for every vertex on this renormalized graph. So in fact, you have these connections all along the way. So this implies that if you have an infinite path in this renormalized lattice, this implies that there exists an infinite component on ZD in itself. So So yeah, we obtain using this one dependent percolation on Z2, because we can define just this on Z2. And the marginals of this process are bigger or equal than 1 minus 2 epsilon. So this is a very, this is super percolating. We just need this to be bigger than 1/2. So this is percolating. And this percolation implies the percolation on slab. So on the slab Sn or S2 anything. So we have proven that it percolates. And yeah, if you want to show some, I mean, we can conclude, I mean, for most of you that are from interactive particle systems, you know that if when this happens, you can use ligation and Stacy and everything is okay. But since everything is, I mean, on Z2, we can control the interfaces very well, and polynomial graphs, we are able to do the same in a different way. You can just conclude in any way by using a Peyer's argument to show, for example, in the main theorem of Chayes and Newman in this context. And yeah, in the polynomial growth case, there are some caveats to this argument, because cut sets are not connected itself, but you can work your way to actually prove the same kind of result on polynomial growth graphs. So I mean, that's everything I think I wanted to say for today. And if you have questions, please don't hesitate to ask. So thank you.
So thank you, Daniel. So are there any questions? So I have a few, but feel free to skip those. I mean, one of them I have is how robust you think the argument is for dependent percolation models, even on ZD. I think it's more. Oh, there is maybe a question in the chat. Oh, there's a question actually from Shangji. Can you tackle that one?
Exponential.
Is
yeah,
the
for
exponential
most,
growth?
Yeah, that's a good question. We were aiming to prove, but for our argument, it's not enough, especially because the geometry of these graphs it's quite. I mean, the main argument in our. So how you can translate all this argument of polynomial growth is saying that these polynomial growth are quasi-isometric to nilpotent, to Kelly graphs of nilpotent groups. And on nilpotent groups, there is a way to map this graph by a surjective map to Z2. So many of the Z2 properties, for example, having a lot of independent paths that goes that cross the ball, or many properties of Z2 can be taken to this nilpotent context or polynomial growth context. In sub-exponential growth is not. We don't know how to do that, and so there are some things you can prove, but it's not. We don't have all the pieces to actually prove the sharpness in this context. So it's a good question, and it's still an open question. I mean, many open questions are open in this case.
And what about dependent percolation?
For dependent percolation, I think many of the arguments work okay. There's no many restrictions about it. We didn't try, but I think most of them is not critical in any of the argument we use, I think. Yeah, I would say it's possible to do it. Yes.
Yeah, the Hamming distance argument one has to adapt a bit, right?
Yeah, but I mean that's maybe the hard part. Yes.
Yeah,
But
especially
I
if your
think
decay and
there's,
interpolation is coming from IIDs, right?
yeah,
Like factor of IIDs or something. Another question I have, for example, one result I proved some time ago was for graphs of polynomial growth, but transitive graphs of polynomial growth, and then someone said, no, but what we did is trivial for graphs of transitive graphs of polynomial growth, and they gave an argument. I said, okay, I have to break some hypotheses to make it more appealing. And then I found out about roughly transitive graphs.
yeah,
Graphs that are not exactly transitive. So you break the whole algebraic arguments, and you still need to prove things. If you need I mean, don't break the probabilistic arguments. You think you can also get away without any algebra? Like this
yeah, I remember
rough
that.
isomorphism too.
Yeah, I think, I don't know if, because many of this result depends on this map, on this algebraic map that you can construct 2Z2. So, I mean, this geometrical structure is somehow really relevant to prove that. But, yeah, and also even the self result, I mean, these two arm events is somehow that is not trivial in the polynomial growth case. And I think most of the time we spent was reproving that on polynomial growth case. So yeah, if you know somehow, because this paper decomposes, I mean, this work decomposes in many little pieces that are, so you have this all these arguments of sharpness and sharp thresholds, you have the arguments of self, and you have the geometrical arguments that goes together. So we need to check that. I mean, probably not, it doesn't work directly, but if you are able to reconstruct all these arguments separately, it can.
Interesting. Are there any more questions? So if not, let's thank Daniel again. Thank you.